Hello, good morning everyone. My name is Marko Guberina and my final thesis is Singularity-robust manipulator path following. Let's deconstruct this title so that we know what's going on. A manipulator is just a robotic arm. A path is a curve in space to be followed by the tip of the robot, which is called the end effector, and singularity-robust in short means reliable. Here's the roadmap to the presentation. Alright, so first let's describe the problem a little more formally. So why did I say that singularity avoidance means reliability? A singularity is a point in which the manipulator loses the ability to move in some direction, and in some tasks such as welding it is absolutely essential that we avoid this. So that's why we will produce a kinematic controller, a piece of software that controls the arm so that it avoids singularities. Now to begin our quest to obtain the algorithm, we first need to formally describe the robot. The robot is a series of rigid bodies which are called links, and they are connected with joints. Joints can be revolute, they can be prismatic. We will focus on revolute joints because that's what's most often used. Okay, so then what we do is we do not describe the whole of the robot in one frame, but we describe each individual joint in its own frame to make the math easy, and then we use transformations between those frames to know what's going on in the base frame. The formulation of rotation used in this thesis is rotational matrices because they are easy to understand. And along with rotational matrices, we have translation vectors, and with these two pieces of information we can completely describe another coordinate frame, and we combine this into a homogeneous matrix. The way we define coordinate frames is via the Denevit-Hartenberg convention. Okay, now that we know what the robot is formally, we can answer the question of forward kinematics, which is where will the joint go, where will the end effector go when we move joints by some angles. So it's a map from joint space to operational space. The operational space is the 3D natural space. Okay, so what we do is we calculate the rotation in the frame which is closest to the end effector. We then map that back to the previous joint, calculate again, and so on, and we get the position of the end effector in the base frame. And that's this expression here. Now that was easy, but what we actually want is inverse kinematics. So telling so we have a point where we are. We want to move to another point, and we want to know how do we need to change the angles to get to that point, and that's inverse kinematics. So for redundant manipulators, meaning they have more degrees of freedom than free, we will get an infinite number of solutions, and the dimension of the solution will be n minus 3. So to obtain unique solutions, we'll have to reformulate the problem as an optimization problem, and then what we'll get as solutions are iterative calculations, or an iterative algorithm which moves us to the point. So basically we will move bit by bit until we reach the desired point. What will help us do this is the Jacobian, which maps small changes in joint space to changes in end effector position. Now why small? Small because the map in general is not non-linear, but if we take a snapshot of it, we get a linear operator, which is the Jacobian, because it's a matrix. And then we can use this to solve the problem. Okay, so now let's see how this works as an optimization problem. Here we have what's essentially kinetic energy for the joints. We want to minimize that, and we want to do that in a way which respects this constraint, which is that the end effector can move in such a way which was described by the Jacobian. So basically we want to move as little as possible. This specific formulation is called the quadratic programming formulation, but there are other ones. Okay, so the methods we have as results are the Jacobian transpose, which basically here pretends that the transpose of the Jacobian is its inverse. It works fine, but of course, since it's not, the Jacobian transpose is not its inverse, it works not too well. Now the second thing we could do, having this equation here, is to have a pseudo-inverse of the Jacobian, and while that's a good idea and it comes up as a solution when we define the problem as a linear optimization problem, that method suffers from high instability near singularities and cannot be used in production. Next, we have the damp squares method. It basically introduces a damping factor to the previous method so that it becomes stable near singularities. Now, the reason why it's unstable is because when we try to do a pseudo-inverse of a matrix which has a null column, we will get undefined, and the solution will blow up to infinity. So that's why the damping factor is introduced. However, with that we lose the ability to use the pseudo-inverse null space projection for adding additional tasks. So while this is in a way singularity robust, we will actually use the quadratic programming formulation because it allows us more flexibility and solves all of the thus far mentioned problems. Okay, so now we can talk about trajectory following. Basically, we take the curve in space, we then splice it into points, and we use inverse kinematics algorithms to go through those points. Now, if one thinks that then the robot will really move and stop, that's okay, but we can have this algorithm work in such a way that the next point to be reached is generated before the manipulator slows down. So that's why this works, and it's as precise as possible as trajectory generation. Okay, so now we can talk about manipulability. Manipulability is it will help us more formally, more precisely, more deeply define the singularity, because it's essentially a dual problem to the problem of singularities, meaning that when we have a singularity we cannot move in some direction, and manipulability tells us how easy it is for the robot to move in some given direction. So this is reached by taking a unit sphere in joint space, mapping it into operational space, and then see what the result is. So the result is an ellipsoid, and when we have an ellipsoid of this shape, this means that it is easy for the manipulator to move here and harder to move here. And we will use these ellipsoids to avoid singularities, as will be explained shortly. So basically we have a matrix, which is this matrix. It describes the ellipsoid. Then we do eigenvalue decomposition of it, and the eigenvectors tells us the principal axis of the ellipsoid. And basically, in order not to be in a singularity, we want that that no principal axis has length 0, meaning that then the ellipsoid collapses, and that's what we want to avoid. So basically we'll use these ellipsoids to change the current manipulability into, so to transform the ellipsoid into something else, and by doing that we will avoid singularities. Now the problem with this approach is that the space of symmetric positive definite matrices, which define the manipulability ellipsoids, do not form a vector space, meaning that we cannot add two of them together and have the result also be an SPD matrix. However, what we do have is the fact that SPD matrices form a cone in space, meaning that all possible ellipsoids live on the cone. And then what we do is we define differential geometry on the cone so that we can compare different ellipsoids. So basically we need that. Okay, so there's no way I can explain what Riemannian manifolds are in 2 minutes, so I won't really try. I will just explain how this works. So essentially, we have the cone. We have our current point on the cone, which is a current manipulability ellipsoid. We then find some other ellipsoid on the cone toward which we want to move, and then we have all of the necessary mathematics which describe how the lines on the cone between these 2 points, and we use those lines then to move in the direction of those lines and thus change our manipulability. If this is something that interests you, I have written extensively about it in the paper, and I have mentioned the literature, so you can check it out. But basically what is done is we want to scale the current ellipsoid so that the smallest axis of it is always stretched. We do this by finding a sphere, and we move towards the sphere. When we move towards the sphere, which is bigger than the current ellipsoid, the smallest axis will always get stretched, and thus the singularities will always be avoided. What we do is we find a geodesic between the current ellipsoid and the desired sphere, and then calculate the gradient on the motion from the current ellipsoid to the sphere, and we use that vector we basically shove that vector into QP formulation, and we get manipulability, maximization, or singularity avoidance in the inverse kinematics algorithm. So this is how you compute parts of the vector, and then we put it in the QP formulation like so. And this way we always stretch the ellipsoid towards the sphere, and we always avoid singularities, which are points where the ellipsoid collapses. Okay, so now let's talk about results. I have some video presentations here. Basically, I hope this will make things a little more clear. So here is an inverse kinematics algorithm performed with the Jacobian transpose. As you can see, this is a rather uncomfortable position, meaning it's close to a singularity. But if we use singularity avoidance, then this is the result we'll get. So as you can see, the manipulator now is in a much more comfortable position, meaning that it's less likely to hit a singularity. Now, as you also could have seen, the manipulator went a little wild at the beginning. That's because the parameters of the model are not fine-tuned, as they didn't have the time to do this, but I think that the result speaks for itself either way. Okay, so now we do the same, but for following some, for following some curve. Oh, I am having tapped one. Okay, there we go. So this is how a pseudo-inverse would follow this curve. Okay, and now what we have as a result is this. So as you can see, the position of the pose of the manipulator is changed so that it can follow the curve more easily with higher manipulability. Okay, so the results are the controller written in Python with NumPy, the simulation which was done in VBots, and yeah, okay. And now the conclusion. The conclusion is that the concept of manipulability is extremely useful because we can not only avoid singularities but maximize manipulability in different ways. So if we want to maximize force manipulability, we could do that, and then the robots would be able to push in with smart poses. We could also define some statistics on the manifold of the SPD matrices, and then we could learn manipulability. We could stabilize bipedal robots by maximizing the manipulability of the center of mass, and so on. So the framework is very general, the differential geometry framework. It allows us to do many things, and what's explored in this thesis is just really the tip of the iceberg with this approach. However, the developed controller is useful. The only things that need to happen in order for it to work is the fine-tuning of the parameters to the specific arm which is used and the specific production environment. This has been my presentation. I hope you enjoyed it. I will now be answering questions, so please feel free to ask me anything about this, as this presentation has been really cut down and there's a lot more to say about the project. Thank you.